Okay, so why don't I start? Can you hear me in the back okay? You guys over there? Okay, good. So to continue where we left off last time, let us go through the physics of recombination so that we can understand what time period we're looking at when we look at an image of the CMB. Okay? So let's discuss the physics of recombination. And I'll explain what that word means in a second. And also, so last lecture, I put a few equations up which I didn't derive from first principles. If any of those equations are confusing, just come talk to me in a coffee break and I can point you to the derivations. It's only that if I had derived all of them, we wouldn't have time to get to the interesting things. But if any of that's confusing, just come and find me in a coffee break. The few things that I didn't derive are actually straightforward to find in a textbook. Okay. But ask at any point. Okay, so why do I say recombination? So the period that we're talking about when we talk about the time period we're looking at when we look at an image of the CMB, that period is called recombination. And it's a sort of misnomer because, first of all, what's being combined is electrons and protons to form a hydrogen atom. That's the time period that we're talking about. We talked about BBN before, where nuclei were forming for the first time, anything beyond hydrogen. And now this period is going to be the first time we form atoms. So that's why there's the combination, but the re is just nothing. Atoms didn't form before that. And so it's a little bit of a misnomer. Maybe people were working backwards. Whereas there's something else later called reionization, and that's when the universe that was ionized originally forms atoms and is no longer ionized, and then stars form and it reionizes the universe. So that re is fine. This one is a little weird. Okay, so now the question is, when does recombination happen? Recombination. But we're just going to call it recombination because that's what everybody calls it. So when does it happen? I'm actually usually very interactive in my lectures. If I say when this has happened, is somebody going to shout out and give me a guess? Or not? I don't want to take up too much time, but is there any quick guess of, like, if I had to say when would a hydrogen atom form, what would you tell me in terms of
temperature below binding
temperature below
the binding energy?
Right. So the same way with BBN, that could only happen when the temperature was actually below the binding energy of deuterium. So someone had asked me in the reception yesterday, and I didn't go into BBN in detail, but deuterium is the first building block in order to get the chain reaction of BBN happening, and deuterium has a very small binding energy. So you need the temperature to fall below the binding energy of deuterium. In the same way, the temperature needs to fall. So what's happening during this time period is you're having an electron and a proton. Now, like, the proton is going to capture the electron and form the hydrogen atom. Okay? That's the key physics that's happening during this time period, and you want to have the photons that are surrounding this electron and proton to have energies that are lower than the binding energy of this. So you know that when the electron and the proton bind together, they're going to release 13.6 eV of energy when this is in its ground state. And if you have a photon that comes along that has 13.6 eV of energy, it's just going to ionize the atom again. Okay? So you would sort of do a quick calculation and say that it would happen when the mean energy of the photons, and the reason why I define the mean energy of the photons, so when you have a black body, this is the formula for the energy of the photons. So it's related, the mean energy of your photons are related to the temperature by this, if you have a black body. So you would say you want HF mean, that's the frequency of the photons, to be less than 13.6 eV. So then you might tell me that that happens, so the temperature of recombination, you would tell me happens at 13.6 eV divided by 2.7 K. So you would tell me it happens when the universe is 60,000 degrees Kelvin. Okay? Yeah.
Just assuming there are enough photons to do it, just a bit confused about that I'm sure that this condition found enough photons to always react.
No, this is wrong. And so I'm going to tell you why it's wrong. So this would be the wrong answer. And why is it wrong? So to first order, what would be a reason why this would not be sufficient? If you think about a black body spectrum. Yeah. Exactly, right? So your black body spectrum, and if it was the right answer, I'd be done. And because it's the wrong answer, thus we have lecture 2. So that's basically. So the black body spectrum's got this tail, right? And there are a lot of energetic photons out here. So calculating what the mean energy is, which might be somewhere around here, not drawn to scale, isn't good enough. And why? What's the other piece? Does anybody remember something that we calculated last time? A lot more photons. So last time, what we calculated was that the eta, which is our photon to baryon ratio, so this, well, it was the baryon, let me write it like this, it was the number of baryons to the number of photons, was 5 times 10 to the minus 10. So that's what we spent time calculating last time. And that means we have a ton more photons to baryons. So because of this tail, and because we have a ginormous number of photons in relation to baryons, you need to go well below this temperature to not have photons anymore that are going to ionize these atoms. Okay? Okay, so I can put this up. So now we want to calculate this temperature. So we are going to expect that this temperature will depend on the photon to baryon ratio, how many photons there are to baryons, and let's call Q this binding energy 13.6 eV. Okay? So these are two things that are going to go in to determining this temperature. So how does the calculation actually go? So the reaction that we have is that hydrogen plus an incoming photon is going to ionize the atom, and we're going to get that, right? So we've got this reaction going back and forth. And we want to know, we're basically looking for when this process freezes out, basically, right? So when it's in statistical equilibrium, then the way that you proceed with a lot of the calculations in the early universe is that you use Boltzmann equations. And what I mean by that, so say this reaction is in statistical equilibrium at temperature T, then nx, which is the number density of any particle I'm talking about, whether it's hydrogen or the proton or the electron, this nx, which is the number density, is given by the Maxwell-Boltzmann equation. Okay. So in particular, what we would say is that the number density of whatever I'm considering, whether it's hydrogen, protons, electrons, my massive particle, is given by the degrees of freedom of my particle times mx kt 2 pi h squared 3 halves, and then with an exponential factor here. So minus mx c squared kt. This is only the case if kt is much, much less than mxc squared, right? This is only a special case of the Maxwell-Boltzmann equation, yeah.
So can you tell a little bit more about what's the statistical equilibrium compared to chemical equilibrium?
Oh, I'm using that all pretty much interchangeably in the early universe. So, I mean, it's all in thermal equilibrium here. What are you thinking about the distinctions between chemical, thermal?
Yeah, because normally we're going to use the Boltzmann equation in order to get the number density, even when the system is not in the thermal equilibrium. But it does not follow the thermal equilibrium track. For example, in the case of freezing out.
Okay.
So that's,
Okay. Let us call this then in statistical equilibrium. That's a good point. Let us call this in statistical equilibrium for this case, but I don't.
oh, sorry.
Yeah.
I was talking about Boltzmann equation, but you're not talking about that.
This is just the Maxwell-Boltzmann
so
formula,
that-
right? For here, I don't think that we have to worry about that.
Yeah,
For
I agree.
other calculations, like if you're thinking about dark matter freeze out, you want to pay more attention to these things. But for this purposes, I think it's just pretty straightforward. And we've just got a reaction. Let's just call it statistical equilibrium here.
That's right.
This assumes thermal
I
equilibrium.
just got confused with the Boltzmann.
Right.
Yeah,
Maxwell-Boltzmann equation
Yeah,
here.
that's right.
Okay. Here, the G will be if we have electrons, protons, or neutrons, then we have 2. But for hydrogen, G is 4, okay, for the degrees of freedom. All right. And that's because these guys have 2 spin states. 2 spin states. Okay. Now, a convenient thing to do is then to take this ratio of NH to NP and E. To make this go up, okay. Is it hard to see the other board? Which one is hard to see, just so that I know? Oh, it's hard to see the bottom. Okay, so when I'm finished, I'll push it up. Okay, great. Okay. So if we do GH, GP, GE, then this cancels. Oops. And here we have MH MPME. And this piece is going to be pretty much equal to 1 over ME to the 3/2. Because in this ratio, the difference between the hydrogen and the proton mass is not going to be important. Here we have KT 2 pi h squared minus 3/2. And then here in the exponential, we're now going to have the mass of the proton plus the mass of the electron minus the mass of hydrogen, c squared, divided by KT. That piece here is what we call Q. That's the binding energy, right? It's the difference in energy between these guys separate versus in the hydrogen atom. So when we write this ratio, NH, NP, and E, we get MEKT 2 pi h squared minus 3/2. And then we've got this exponential, QT. Okay. This equation, we call this the Sehgal equation. And it's going to tell us how our ionization fraction changes as the temperature changes. So this ratio is giving us an ionization fraction, like how much hydrogen to protons and electrons. And you see it's going to depend on Q and the temperature. However, the equation in this form is not so useful for us. So we want to put it in a form that's more useful and that also depends on eta and Q. Well, we have the Q, but also depends on the eta. So let's rewrite this. Okay. So we're going to define something which we're going to call X, big X. And we're going to let X be the ratio of protons to the ratio of protons plus hydrogen. So this bottom piece is basically all of our baryons, because our baryons are either in protons or hydrogen. Remember, we actually don't have any free neutrons anymore because they all decayed after 15 minutes. So all our baryons are in here. So then, okay, so let X equal this. Then we have X equals NP plus NH equals NP. And now we're just going to do a little bit of algebra to get to where we need to go. So we're going to have X and H is going to equal 1 minus X NP. And then we're going to have our NH equals 1 minus X over X NP. And we're also going to remember that NE equals NP because, as we said before, the universe is neutral. Right, so we want these two to be equaling each other. And then we can write NH over NP, which is basically going to be our ionization fraction, as 1 minus X equals NP ME KT divided by 2 pi h squared, 3 minus 3/2 minus 3/2 exponential Q over KT. Okay. The thing now that we want to eliminate, so this is going to be our ionization fraction. We want to eliminate this NP because I don't know what NP is. So in order to do that, we're going to use the fact, we're going to replace it with eta. So eta is our total number of baryons to photons. And that means that this is NP plus NH to our photons. And that means I can write it as NP divided by X divided by our photons. Because don't forget, X equals NP plus NH. Okay. Now, since the photons have a black body spectrum, so since black body, then I know what the number density of photons are in terms of temperature pretty simply. So that's given by 404 pi squared kThc cubed. And that I can write as 0.243 kT cubed. Sorry, kTh cubed. Okay. So now I put that in here, and I've got MP in terms of eta and this business, temperature. So this implies that NP is given by 0.243 x eta kT hc cubed. Okay, great. So then, the equation we want is 1 minus x is given by, I hope you guys can see over there? Okay. Is 3.84 eta kt mec squared 3/2 exponential qt q over kt. And this thing, so this is the equation we want. This is just the Sehgal equation rewritten. And what people often do is write this as, so this is basically some function that's a function of temperature and eta, right? So I have here a function of temperature and eta, and I can vary temperature and eta or hold eta fixed, and then I can figure out what my ionization fraction is. Okay, this is the equation we want. The solution to this equation is that you have x equaling minus 1 plus or minus plus 1 plus 4s divided by 2s. 2s. So now I can just vary this function as a function of temperature and eta, and I get my ionization fraction. Okay? So now the question is, what is actually the definition of recombination? Because people are sort of loose with the term, and when people say recombination, they actually mean what we call photon decoupling, which we're going to talk about next. Just as we talked about neutrino decoupling, there's a period where photons are going to decouple. But technically, recombination is, well, it's an arbitrary definition, but technically it's not the same as photon decoupling. And you can have an arbitrary definition. So say if we define recombination as when x equals a half. So what I'm saying is, let us define recombination as when half of all the baryons are ionized and half are in hydrogen. Then if we solve this, we're going to get that the T of recombination, so given that same eta that we had before, that 5 times 10 to the minus 10 for eta, so we just keep eta fixed, and we've solved for the temperature when x equals a half, then we're going to get that this is going to be a temperature of 3,740 Kelvin. That's much less than the 60,000 Kelvin we were talking about before. And if you want to talk about what redshift this is at, then this would be at 1370. And if you're talking about time in years after our Big Bang, then we're talking about 240,000 years after the Big Bang. That's when half of all the baryons are in hydrogen and the remaining half is ionized. The reason why people are a little bit fast and loose with their definition of recombination, and they kind of mean photon decoupling when they say it, is because while you get to x equals a half at this time period, between here and 100,000 years, basically everything goes into hydrogen. So you have just 100,000 years or 150,000 years, and quickly everything goes into hydrogen. So the time period, so in the grand scheme of things, people just equate recombination to photon decoupling. Photon decoupling is going to happen shortly thereafter. Okay, so the picture that we have that's happening is the universe is cooling down. All of a sudden, those hydrogen atoms are forming and they're not getting ionized again. By this period, things have cooled, the photons have cooled so much that half of all the protons are now in hydrogen atoms. And now what you can imagine is going on is, before we had this very opaque medium where every time a photon was trying to move, it would scatter off a free electron. Now what's happening is that when it tries to move, so imagine you had this whole soup here of free protons and free electrons, and every time a photon tried to move in any direction, it was scattered back again to an electron, and then it hit another electron and was scattered back, and it had a super tiny mean free path. Okay? Now when the protons capture the electrons, they bind the electrons to them really tightly, right? And so now the electrons don't have this large phase space that they can be around. They can be here and here. And when you get to basically 100% of everything in hydrogen atoms, then your photon moves and it doesn't scatter off of anything. And you do have so it's not a delta function, there's some width, but over a very short time you do have this big, relatively discontinuous jump where the mean free path of the photon goes from being super tiny to being basically the size of the entire universe. So now this photon, whereas couldn't even move an inch before getting scattered, can travel all the way to us, basically not being scattered at all, pretty much. Okay? That's what we call photon decoupling. And when we take a picture of the CMB, we're taking a picture of this epoch of photon decoupling. basically, the other word that we have for it is called the last scattering surface. It's basically the last time the photon scattered off an electron and then came all the way to us. Okay? When I give public talks, I always like to describe it as, you know, if you're looking up at a cloud layer, here's your layer of clouds. You know, on the, well, here in Boulder, I don't know what you see in clouds, but on the East Coast, it's very easy to look out the window and say, okay, we have this solid layer of clouds. And imagine that that's your CMB surface, because that's what you're looking at when you're looking at clouds. You're looking at the last scattering surface. And basically, you're looking at the place where the photon scattered last and is coming to you, and you cannot see any of this stuff up here. You cannot see through the cloud layer. You always just look at the last scattering surface of cloud. Okay. Now, to calculate when photon decoupling happens, let me make a brief aside. Let me keep track of time. Okay. It's 2:30, so we go till 3:15, right? Yeah, I got the. Okay. Okay, so let us have a brief aside here. Because with photon decoupling, we're going to, the same way as before we were calculating rates related to the Hubble expansion. And last time, what did we say last time? We said that the rate was much, much bigger than h, right? So we said before, when a was about 10 to the minus 4, 10 to the minus 5, we said the scattering was much, much bigger than the Hubble rate, and that's why the photons and electrons were tightly coupled. So in order to calculate decoupling, what we want to know is when this rate becomes less than h, and to first order, let us calculate when the rate equals h, right? Actually, when the rate equals rate h, shortly thereafter, you get this, and you have photon decoupling. So we want to calculate the correct h, which is why we're having a brief aside, because before, when we calculated h, we were safely in the radiation-dominated regime, right, where radiation was dominating the dynamics. And I wrote an equation down, which maybe not everybody was familiar with. So I had sort of cavalierly said h squared over h naught squared equals this. And then I got an h, right? This is from the Friedmann equation, which is just taking the FRW metric and then putting on the other side, using Einstein's equations and putting on the other side your energy and matter components, and you get the Friedmann equation. Definitely Cosmology 101, probably everybody's seen that. Okay, so we want to know what the equivalent equation is now when we're trying to calculate photon decoupling. So, since the matter is going to fall like a to the minus cube, the matter density, or the matter energy density, which is just this times the c squared, that's just because the amount of matter stays the same, but the volume increases. So the density is going to fall like a to the minus 3. And the radiation is going to fall like a to the minus 4, because it's the same a to the minus 3 volume factor, but as the universe expands, each photon's energy, the wavelength gets stretched. So the energy, so here is actually where I shouldn't be so sloppy in calling it density. What these are is the energy density. The energy density, where I mean rho c squared and rho radiation c squared, basically. So equivalent. So the photon energy falls as a factor of A. What might you think happens after a period of time? The universe starts out radiation dominated, but what happens? Say that again? Right, because at some point there's going to be a crossover. And let me put my rows back just because C is 1 here. It's probably a rule, right? C's are 1 in TASI or something like that. Okay, so when are the two equivalent? And it's important to know this because before I can write approximations like this where radiation is dominating everything, but I need to know when that approximation breaks down. We call this epoch the matter radiation, we just call this matter radiation equality. And to figure out when this happens, the thing to note is that omega matter over omega radiation is proportional to a to the minus 3, a to the minus 4 equals A. Let's see. Let me leave this down like this and go to the other side. Let me just write a few things here. So I could write rho matter equality divided by rho radiation equality divided by rho matter today, rho radiation today, and I would say that it equals A equality. And is that clear? Why?
A is 1 today.
So A is 1 today, so then I can divide this by A0, which equals 1, right? What else? This guy equals what? That ratio? 1. So that equals 1. And this equals what? And both of them equal A, right? So this ratio equals A equality, this ratio equals A naught. And there we go, right? So to know when the size of the universe at this epoch of matter radiation equality, what I need to know is actually the density in radiation and matter today. R0, M0. Okay. So today, what is the density of radiation? So this was, I think, leading up to one of the other equations that I didn't derive last time. So this isn't a generic equation that you get just by considering any sort of relativistic plasma. So never mind the zeros right now. This equation will always be true, and this is just StatMech. Use your phase space distributions for photons, and you're generically going to get this out. And I guarantee you, it's even in I think it's probably even in old cosmology textbooks. And what changes is that as the universe cools down, you're going to have different particles. So very early on, you're going to even have like your W and Z bosons and your pi's, etc. That's going to change G star. When you have your E plus E minus going around, that's also going to go into G star. After all of that, and after E plus E minus annihilation, the only thing that you're left with that's contributing to the radiation is photons and neutrinos. Okay? So today, I'm going to put 0 and 0 here. This is my photon temperature day and my radiation today. So just have photons and neutrinos. And the reason why we say this G star number is 3.36 is it equals to 2 for photons plus our 1.36, which is not the degrees of freedom for neutrinos, but we take into account that the neutrino bath is at a different temperature. So if we're doing G star with respect to the photon temperature, then it comes out that effectively the effective G star of the neutrinos is this, if you're defining it with respect to the photon temperature. Okay? Otherwise, if you're defining it with respect to the neutrino temperature, it would just be 2. Okay, so now all I need to know is what's the temperature of the photons today, which I know. So then I get that the radiation today is 7.8 times 10 to the minus 34 grams per cube. That factor is there too. So when you do the statistics and you calculate the phase-space distributions, thank you, you're going to have to note that the photons are bosons and they've got that distribution, and the neutrinos have the fermionic distribution. Yes? No, because equality is so late that, well above equality. At the time of E plus and E minus annihilation, that's when you just have photons and neutrinos left, which was super early, and that's all we have. Nothing else is adding to radiation. As far as we go, although in the very last lecture, I'll talk a little bit about N effective and say something more about that. But for right now, this is fine. And for matter, our density today is going to be so where is this equation from? This is also just from our Friedmann equation. But today, well, let's see. Okay, this is just from the Friedmann equation. So, and this is going to be 1.879 times 10 to the minus 29. And I'll leave it in terms of, often cosmologists leave things in terms of these quantities so that whenever Planck comes along or WMAP comes along, you can just plug in the number here. Okay. But for WMAP, so I wrote, this is slightly outdated. I have in my last lecture the updated numbers. So first of all, what is a megamatter? Let's be clear. Whenever you see this in a Planck paper or a WMAP paper, this is cold dark matter plus the baryons. If it was only cold dark matter, you see a C here. And from the old WMAP results, this was about 128, something of that order. So given that, I can calculate when the equality happened. Let's see. Wait. A bunch of boards here.
Can you please raise the board behind this one?
Raise this one?
Yeah, that one because we didn't have this.
Okay. This is new for me.
Sorry.
No, it's great. I wish I had this in my class. Okay. Very good. Just definitely ask me questions if I just sort of say things and assume everybody knows what I'm talking about. So H is basically H naught divided by 100 kilometers per second per megaparsec. So H naught is in these units, kilometers per second per megaparsec, and then this is just divided by 100. So usually this is about 0.7. This is actually slightly outdated. This is the way it'll be in the Planck and WMAP papers, but just as an aside, sometimes you'll see this, which is H naught divided by 70. And you'll usually see a little 70 here. And can trip you up if you don't know what's going on. But that's just because everybody's so tired of dividing by 100 when they're like, look, we know it's 70, so just tell me. It's much easier to then process numbers without having to mentally divide by a 0.7 or 0.7 squared factor. So people switched to this convention so that every number was much more transparent. But anyway, that's just an aside. Okay. So A equality is basically going to be about 10 to the minus 4. That gives us a 1 plus z of about 3,500. And the temperature of the photons at equality, well, I have it in terms of this. That's what the EV is. So before, when I had picked a number of 10 to the minus 4, and I said, let's calculate the coupling rate, that's because I already knew I was well within the radiation error. But if you look at this Z here and compare it with the Z of recombination, well, it's not, well, what you see is that we've already passed the epoch of matter radiation equality, right? So we calculated there when is half the universe in hydrogen and half in protons. And we said over here that it happens at a Z of 1300, right? But the reason why we had this whole aside is so that I could tell you, but at 3500, what happened was now matter has surpassed radiation in dominating the dynamics. Okay? And so thus we had a long aside so that when I calculated H to figure out when photon decoupling happens, I could use the right H. Okay, so when does photon decoupling happen? So let us see. So can I bring this down and write on that one? So this happens relatively quickly after we get to that h is a half thing, within 100,000 years. So we need to calculate the rate. So let's calculate the rate as a function of z of scattering. This is the rate of photons scattering off of electrons. Rate of photons scatter off electrons. So it's going to depend on the density of the electrons, on my Thomson or Compton cross-section, whatever you refer. And that's going to depend on our big X times the density of baryons today, 1 plus z cubed, and then my cross-section times c. So why? Because so remember that X here is my protons to my total baryons, okay? And Ne equals my protons. Ne equals my free protons, because the stuff in the hydrogen atom is in here, in my baryons, okay? So if I want this, then I've got X times N baryon, but that's N baryon back then. And if I want N baryon today, then I have to divide by A cubed, right? So N baryon today is divided by A cubed. And we remember that A is 1 plus C. Okay. Let me write on the bottom here. Let's see. So we're going to use that omega baryon today is about 0.04, and we're going to calculate what the rate is. Let's see. Let's do it over here. Or actually, let's see. You can put this up. Can I erase that? I've forgotten now. 3 Bohrs is sort of complicated. Okay. Okay. All right. So our rate is going to be 4.4 times 10 to the minus 21 inverse seconds times our x of z and our 1 plus z cubed. Yeah.
So the ME and NE have slightly different, right? Because you keep putting the exponential.
Because the universe is neutral. So if I had free protons that did not have the same density as free electrons, then I would have some overall charge.
Yeah, but if you follow the full distribution, so they're exponential. And the M is different. So slightly.
For the electrons and the protons, let's talk about that over coffee, but I'm pretty sure you can't have an overall charge to the universe. So let's talk about that definitely over coffee. Right. So that's one way to think about it, that if you have things going like this in our equation, then you're always going to have equal numbers of the free guys over here. All right, but let's definitely talk about that if something is still confusing. Great. So now, what's our H? So now I know that what I can do is just write this as omega m0 a cubed, because I'm firmly in the matter-dominated regime. Okay, my redshift is 1370. I said I had a quality at 3,500. I'm well in the matter-dominated regime here. So now I can say that this is 1 plus z cubed. And if I use now, flipping to the back of the book here, because I know that the matter today is roughly 0.3. I mean, not even from the CMB, even from galaxy clusters, roughly, we've known this for a long time. Then I can say that my H is 1.24 times 10 to the minus 18 seconds, 1 plus z 3/2. Okay. And now if I equate the two, that's going to tell me when photon decoupling happens. So let this rate equal h of z. Then I get 1 plus z decoupling 3/2 equals 43 3/2, and then my x factor as a function of z decoupling here. Therefore, my 1 plus z decoupling equals 43.0. So you can solve by plugging in an X where basically everything is ionized, and what you get is that Z of decoupling equals basically 1100. T of decoupling is about 3000 Kelvin, so way lower in temperature than the 60,000 we had calculated before. And the time is about 350,000. Okay. So this is the info. When we see the picture of the CMB, we're taking a picture of this epoch. And yes, even photon decoupling doesn't happen as a delta function, but the width is pretty thin compared to the grand scheme of things. Yeah.
Isn't x of order 1 at this time? X is 1/2 of 1500.
Right. Good question. Let's see. Say that again. X is... Yeah, let's go back to... Yeah. And it'll converge to this. So it's going to drop rapidly. And yeah. Good, thank you. All right, great. So what happened in 1990? So we had left off with the measurements where we had said, okay, Penzias and Wilson, they discovered this 3K background. That's great. So in 1990, a satellite was launched, actually in 1989, called COBE. And the point of the satellite was to say, okay, well, this is all nice, but how do we really know that this radiation is coming from this early universe like like this nice theory says it is? So Penzias and Wilson had measured that 3K microwave background, but astronomers can be skeptics, right? And it's not like there are not other things in the universe that emit in the microwave. So if you only are measuring some mean temperature in microwaves, someone can say to you, well, you know, I have a whole bunch of galaxies that are unresolved all around me. They can have a relatively uniform distribution. How do I really know that that 3K background isn't coming from them, right? So the point of the COBE mission was to measure this temperature as a function of frequency, right? And really see, does it have a black body or not? Because if you have all these astronomical objects, say a whole bunch of galaxies uniformly distributed around us, the emission of those as a function of frequency is not going to be a black body, right? So if you see a black body, that further puts the nail in the coffin that that radiation cannot be from anything else, okay? So in 1989, COBE was launched, and it had 3 instruments on it. So one, which was actually measuring infrared emission. Another, FIRAS, which was going to look for the black body spectrum. And another called DMR. And what DMR was looking for was DMR was making a full map of the sky, so full sky map, and it was looking for fluctuations. Because the theory was that initial fluctuations in the early universe seeded the structure we have today. And so their sensitivity was, predictions had already happened even in the 1960s of the relative amplitude of these fluctuations to seed the structure we have today. So COBE was looking for all of that, and they had 3 big results. So let me write the results here, because then I'll put down a screen over there. So their papers were only in around 1994 or so. So they took a little time. So one was that at every single angular position on the sky, you had a black body spectrum. Okay? So at any position, which we can call theta and phi on the sky, right? Angular position. And FIRAS could detect a deviation at any frequency. It could deviation in intensity of about 10 to the minus 4. So it was pretty sensitive. No deviation found. The other result was that if you looked at their full sky maps, they wouldn't look actually anything like the CMB picture we're used to seeing. And that's because all you can actually see is a dipole. So the CMB has a dipole. A dipole distortion. In temperature. So what I mean by that is that if you look at the picture, of the CMB, so you usually see pictures like this. That's a full sky just projected out. But instead of seeing that like red and blue pattern that you're normally used to seeing, you see more like this yin-yang pattern where you see blue here and red here, okay, in the map of the CMB. And, what?
Sorry.
Okay. I was telling us something cosmically. Okay. So each point, so what's important to note is each position, each point on the sky has the black body. And maybe this is confusing. This is at one frequency, for example. So I pick a frequency and I look at the map and I'll see this. To see a black body, I'll take a point in this map. So I'll take some pixel at theta and phi, okay, and I look at that pixel and I look at it at every frequency. And that I make a plot of the intensity of my light. Intensity is basically synonymous with temperature, so it's just proportional. So I can look at the intensity of my photons or the temperature at that position, and I will get this. Okay? At every pixel, I'm going to get this spectrum. It doesn't mean that the mean photon temperature is the same everywhere. Okay? So at each point on the sky, I have a black body spectrum, but in one half, spectrum is slightly blue shifted. So overall, I'm going to have like a hotter temperature, because remember this spectrum is a function of my photon temperature. So here I'm going to have a hotter photon temperature, here a colder photon temperature. One half is slightly blue shifted, and then the other is red shifted, of course. And who knows why we have that? Right. Say, well, what were you going to say? Right, exactly. So what this is our motion with respect to what we're calling a CMB rest frame. Okay? So this is our Doppler effect. With respect to and there's lots of things that are moving. The Earth is moving around the sun is moving around the galactic center, our galaxy is moving, in the direction of our local group, and then I think our local group is moving to towards some supercluster, so we're moving actually really fast. Okay, so, that's great. just two things to note. This is the most precise measurement of our local motion. People try and do it with large-scale structure, etc., but in my opinion, this is the most accurate one. And then the other thing to note about the phi-res measurement, that's the most precise measurement of the black body spectrum to date. We have no satellites that have measured the absolute temperature since phi-res.
What's our local motion?
I don't remember the exact numbers, but I wouldn't be surprised if it's like a few hundred kilometers per second, at least. Right? Yeah. Nobody trusts the. I would say many people don't trust any sort of local structure measurements. No, it's a good question. So, so the monopole, we would never, we just subtract that out in all of our data. Is there a dipole? Theoretically, I think you wouldn't get a dipole. Theoretically, you would only get, what I mean theoretically is just from, just from linear theory, when you calculate the C and B equations, right? So it's a good point. I'll think about that a little bit more, but I don't think fundamentally there would be any reason for a dipole like this, just from first principles. Just if you think about the linear theory physics that we have, I don't think so, but I can come back to you. It's a good question. Good question. So, okay. So, let me show you a picture now, since we have 1 second left, and then I'll tell you one more thing that Kobe found. So let's see. Press to turn on projector. Good. It'll take a second to warm up, and so I can tell you the third result. Okay, while that warms up, let me tell you the third result. Oh, did I? Okay, screen did. Okay. The third main thing that Kobe found was after you subtract off this dipole distortion. And it's easy to subtract off because if you just take your real space map and you transform into Fourier space, as she was just mentioning, that dipole distortion is just your L equals 1 multiple moment, and you can just filter it out. So it's pretty easy to take that out. And when that dipole distortion is taken out, let's see, there we go. So here I wanted to just impress upon you the Kobe measurement. This is the data at all these frequencies, and this is the best fit to the spectrum, taken from their 1994 paper. So with these measurements, it really laid to rest anybody saying, well, this is just from a whole bunch of galaxies around, etc. The other main result that they had is after you subtract the dipole, subtract it, then what you're left with is fluctuations. And the fluctuations that we're seeing look like this. Now, actually, they didn't exactly look like this because there's usually the galaxy, And sometimes you'll see a picture like this with a big galaxy going through horizontally. But in this picture, the galaxy has been removed, and you can sort of interpolate through. So you see these fluctuations. And if you look at now the mean temperature, so that's the temperature at each point. Then you're going to get 2.726 Kelvin. So after subtracting off the dipole, you're left with a mean temperature of your remaining pixels of 2.726 Kelvin. And your fluctuations about that mean, so that's what these hot and cold spots are. There are fluctuations about the mean. And so this is how I would describe fluctuations, right? Fluctuation at any pixel minus the mean divided by the mean. And if I take now the square of that, because if I average this, I would get 0. Okay, the fluctuations about the mean are going to average to 0. But I'm going to square them. And square root that. So I'm going to square them. Square the fluctuations, take the average and square root that. That's called our root mean squared fluctuations. That's what's of order 10 to the minus 5. Okay, so that's what we mean when we say the fluctuations are of order 1 part in 10 to the 5. That's what we mean. The CMB knows to be to this temperature to 1 part in 10 to the 5. Okay, and for this. And for the first thing with the black body, the Nobel Prize was given for the Kobe results. And in particular, John Mather was the PI for this, phi-res. And George Smoot was the PI for DMR. And they were awarded the Nobel Prize, each of them. And this basically really put a nail in the coffin for the hot Big Bang model. Certainly the black body did. But then what the fluctuation measurements were telling us was really a way to seed the structure we see today. And just to give you a sense of now where we're going with lecture 3, what we talked about before was really the physics of the smooth universe. And that's sort of your cosmology 101, where you have GR and you get your FRW metric and your Friedmann equations. But that doesn't explain the physics of these fluctuations. So to now understand the physics of fluctuations, we need to have perturbations in our smooth universe. We have perturbations in the metric. Before, when we were talking about rho matter and rho radiation, we were basically talking about mean values throughout the universe, right? But now we need to allow for perturbations in all of these things, and perturbations in the photon distribution. And so that's what we'll talk about in lecture 3, because without that theory, you cannot extract all of the rich physics from the CMB fluctuations. And there's a ton of rich physics there. So let's stop here. Talk about that next time.
So the current measurement of the relative speed, like our local speed, does it match the Kobe measurement? Like what you said?
They're a little bit off, and I think that people will trust the CMB measurements more than anything else. Yeah.